Hi, today I want to share a case study of transportation optimization using Sophus considering zero emission zones. Let's first review the business challenge. Hillwell is a pharmacy that has hundreds of stores in London. It delivers to these stores from 2 DCs, and it has a fleet with a mix of electric trucks and diesel trucks. Let's say in a few years' time, the government will introduce a zero emission zone in the center of London, which can only be accessed by electric trucks. And the electric trucks has a limited range, so we need to consider that when it comes to optimizing the routes. Not only that, the diesel trucks cannot even pass through the zero emission zones. So if you look at the bottom right, we have a graph to represent the business problem. The DC can send out electric trucks, and only electric trucks can serve the store A within the zero emission zone. Then from store A, the electric truck can carry on to visit other stores outside the zero emission zone and return to DC. For the stores that's outside the emission zone, you can use diesel trucks to serve. But that diesel truck must avoid the emission zone on its way to other stores or back to DC. The modeling objective here is to first evaluate how many trucks of each type will be needed to cover the shipment requirements. The management is also keen to understand what the best multi-job routes are to minimize the transportation cost based on real travel distance and speed for trucks. It needs to consider traffic conditions as well as the delivery windows of each store. To solve this problem, we're going to be utilizing the vehicle route landing algorithm that Sophus has developed. This algorithm will assign shipment orders to routes and transportation assets to minimize the overall transportation cost. It also considers the delivery window by site, and it can consider different vehicle types based on their capacity, their range, service time, and cost. We can consider real road distance and time for trucks when we run the transit matrix. We can also consider restricted zones by vehicle type by defining site shipment vehicle product level relationship constraints. We can consider both fixed and variable costs so that we can achieve a holistically balanced solution. In this model, we're going to consider multiple scenarios as well. First, we have a baseline where the allocation of stores to the DCs are purely based on distance. Then for the second scenario, we want to try some what-if questions about balancing the volume between DCs. Then finally, we want to visualize our result in different ways. We need a map, we need an interactive dashboard, we need a Gantt chart to show the detail of the routes, as well as a route plan. Now, the two scenarios. Like you can see on the right-hand side of the screen, we have two DCs, one in Enfield in the north of London, and the other one in Croydon in the south of London. These two DCs will split stores between themselves. For the baseline, we want the model to consider based allocation on the nearest DC. But in reality, there might be reasons when we want to balance the volume between the DCs. It could be based on the capacity of each DC, it could be based on cost, it may be availability of labor or storage capacity. Whatever is the reason, we can solve this problem by first running an algorithm called network optimization. This will allow us to change the flow of the network based on capacity and cost balances of different sites. As you can see at the bottom left, we can set up scenario items where we change the capacity of DC2 to be less than 250 pallets per day. And this is a way to create a soft constraint so the model doesn't go infeasible, but also will change the behavior so that DC2 will have a limited throughput. As you can see from the map, between the top baseline and the bottom scenario 1, the allocation of customers have changed. DC2 now shipped to fewer customers. Now, this is only the first phase of the problem solving. We want to be working out the multi-job routes as a next step. Therefore, we can be utilizing transportation optimization algorithm next. To do that, we normally need to take the output of the network optimization result, convert it to a shipment input into the transportation model. We can do this fairly easily on Sophus. And this is utilizing a built-in ETL tool called Dustro. We have our NO model, and the output of that NO model can be read by Dustro and processed into the input for our vehicle route planning model. And that is an automated process, and once it's set up, you don't even need to leave Sophus to be able to run it. It provides a seamless, smooth experience of data processing and converting one model to another. Let's have a look at the model setup. This is the transportation model input. Here we can define the periods. In this model, we have 7 days. We can define the products, sites, business hours. Let's have a look at business hours. Here we use a group policy to define the open hours per day for the DC and the customers. So DC is operating from 6 a.m. to 5 p.m. every day. The customers are opening from 8 to 5 every day during the week. And you can see at weekend, the closing time is at 12. We can look at the shipment data. The shipment data defines the source, destination, product quantity, and order time. This is the output of the NO model. As I was saying earlier, we have a Dustro workflow here that links the NO model and converts the results into the shipment table that we need. So we can just run that here and we would have a refreshed shipments in our TO model. We could also define a transit matrix, which basically provides the distance and time between all the sites for the solver to work out the optimum multi-job routes. We could select whether we use the car driving time or truck driving time. And we can even select the depart time of a typical day so that the transportation condition can be considered. We can define the different type of vehicles. In this model, we have electric trucks and diesel trucks. We define their capacity to be both 26 pallets. We can also define other information such as the maximum distance allowed. The electric trucks would have a shorter range because of the battery charging requirement. We could also define the maximum distance between in-transit stops. We can define the fixed service time for each unloading activity. Here we have some relationship constraints. Here we can define which stores within the zero emission zone cannot be visited by the diesel truck. Finally, we can use the rate table to capture the fixed cost and the variable cost of each vehicle type. We can define the cost by distance and by duty time as well. Let's have a look at the map. Here we have the network optimization results, where we can compare baseline, where both sides are having about the equal amount of stores, to scenario 1, where we limit the capacity of the DC2. Therefore, more customers are now served by the Enfield DC. Let's now switch to the transportation optimization results. We can switch off the network optimization straight lines. This map now shows all the multi-job routes based on the transportation optimization. We could zoom into the electric truck routes. We can zoom into the city center, and as you can see, all of these stores within zero emission zone are now served by electric trucks. To have a clearer view, we can select a certain routes. Let's look at route 5, and this particular route we can see leaves from the Croydon DC, visit that store, and then go to the city center, visit a couple of stores before returning back. And that route is optimized based on the range, the total distance, and the capacity of the truck. We can also see the results from a Gantt chart. Here we can select the pre-saved view, select the scenario, let's say go to the baseline, search. So here we can see by day, by route, what is the breakdown of activities for each route. Let's just zoom into one. So that route 97 is showing when the vehicle will start, when it will be driving, when it will be waiting, and when it will be unloading, and when it will be returning back to base. The same information is also available in the output tables, where we can see the transportation summaries by scenario, or the summaries by vehicles, or the detailed routes. Let's just have a look at the detailed routes. And for this route, 114, we can see it starts from 6 o'clock, and then it visited store 50, 80, 33, 59 before returning back to base. At each of the stop, we can see the time, the distance driven, the cost of that activity, the amount of pallets that's been unloaded. So a lot of detailed information for the user to consume. Finally, we can also create some visualization to report the results. Here is a dashboard I created that tells me in the two scenarios we run what is the total transportation cost, the total number of vehicles used, number of routes created, the total distance traveled, the total output quantity, which is the same between two scenarios. And there's zero shipments and routed, which is good. And we can select which scenarios that we want to look at closely. And this will report how many vehicles by type we're going to need in that scenario, the split of those vehicles between the two DCs, as well as the cost breakdown by each of the route. If you're interested in the details, you can expand any of the graph to see a bit more details. Hopefully, this demo has given you some idea of how transportation optimization problems can be solved on Sophus. Thank you very much.